Cool, right, thank you, yeah. That was a really warm welcome. This talk, FaCSSt CSS and Performance, I've given this talk once in the States, and every American says, this looks like fascist. I didn't notice it until the Americans started pointing it out. I just wonder if Americans have got the word fascist on their mind at the moment. But yeah, FaCSSt, CSS and Performance. Let's look at how CSS can make your site faster, how you could inadvertently make your site slower with CSS. And what we'll be focusing on predominantly is not going to be sort of runtime and animation kind of performance. That would take sort of 3 times as long. We're going to be looking mainly at network performance, how CSS can be a bottleneck to kind of rendering pages and downloading assets for those pages. So real briefly, I'm Harry. I'm a consultant performance engineer. That's what I'm kind of calling myself at the moment. Every couple of years, I just change my job title, and I get different kind of emails that come in. It's quite nice. Dress for the job you want. And yeah, not to sort of repeat too much of the intro previously, but I tend to work with pretty large companies, doing consultancy work, nearly always about CSS, and certainly for the last couple of years, more focused on performance. And there's a particular client on here I want to mention real briefly. Trainline is a fairly large company in the UK that sell train tickets, and they published a really fascinating case study a couple of years ago, which stated that if they could reduce latency by just 0.3 seconds, customers would spend an extra £8.1 million every year. So I helped Trainline on this body of work, and it was absolutely fascinating. It was a really sort of fruitful, very productive body of work. We're not going to mention this case study again, and this really didn't touch much on CSS at all. But what I'm trying to impress upon you here is that just small, minute gains of just 0.3 seconds could lead to an uptick in revenue of over £8 million. So the margins we're dealing with here are absolutely enormous. And hopefully this 0.3 seconds, or this case study, sorry, should help contextualize just what 0.3 seconds could mean for a large company. Anyone who is familiar with my work will probably remember me from CSS stuff. I've written a lot in the last few years on CSS. And like I said, been focusing way more on performance the last 2 or 3 years. But my sweet spot, my kind of favorite thing, is that bit where they overlap. That's my happy spot. So I had a real good time writing this talk and researching some of the topics. It's going to be a bit of a whirlwind tour. It's quite a big talk. There's quite a lot of stuff in here. Hopefully by the end of it, we'll have a really good understanding of what to look out for in our CSS projects and how that can affect the speed of our sites. One thing I get asked most frequently is, why does it even matter? When we're looking at performance, perhaps we should look at things like server infrastructure first, or maybe nowadays it'd be JavaScript performance. Why is CSS such a big deal? Well, if you look at the HTTP archive, you will find that the top 3 of the top 5 contributing factors to start render all involve CSS. The top 3 reasons why pages may be slow to render is all down to style sheets, and that makes complete sense because you need a style sheet to render a page. When we talk about rendering a page, we're dealing with something called the render tree, and this very, very oversimplified diagram is a representation of the critical path. The critical path is the mandatory work a browser has to do to start getting pixels on the screen. The server sends us some HTML, which optionally could have some JavaScript acting upon it, and that gives us the DOM. We can have some CSS sent from the server, which also could optionally have JavaScript operating upon it, and this gives us the lesser-known CSS on the CSS object model. And once those two are built, we can transpose them into what is called the render tree. And it's not until we have the render tree that we can actually begin changing pixels on the glass. So anything, any hiccups, any problems, any issues along this process is going to slow down that time to first render. So this talk is going to be talking about optimizing this process here. The first and by far simplest thing we want to look at is file size, but this is simple, right? We all know that big files take longer to download, things that take longer to download take longer to get to a user's machine, it's going to take longer to render things. So yeah, that's kind of simple stuff. I don't want to talk too much about just big file sizes in terms of network cost. I want to talk about a small case study from a client of mine. Anybody got any idea how long it would take a Moto G4 to parse a 1 megabyte style sheet? That is a complete rhetorical question. I'd be very impressed if anybody knew, but Henry did just put his hand up. A long time, yeah. A very long time. I've got a client. Who said that? 20 seconds? Oh, not that long. Okay, I'm going to suggest we stop guessing because we've only got 45 minutes. Right, I've got a client who actually does have a 1 megabyte style sheet. They've got this huge WordPress install, and every plugin in the world is put on this website, and it all just gets munged into one huge style sheet. This leads to sort of network delays on the server, oddly enough, but what ends up happening is when it arrives on the machine, it takes 200 milliseconds just to parse that style sheet, just to parse it, not to apply the styles, not to build, not for any kind of a recalc style events. Just parsing that style sheet takes 1/5 of a second. Now remember, 0.3 seconds is worth 8 mil to a certain company, so this is worth a fraction of that. This is a huge amount of time. But 200 milliseconds still doesn't feel very humanized to me. So what I decided to do is put this 200 milliseconds in slightly more human terms. In 200 milliseconds, light could travel 60,000 kilometers. And then I realized that I don't even know how far 60,000 kilometers is. So now I've got to humanize 60,000 kilometers. Light could have done 3 lengths of the Great Wall of China in the time it took a Moto G4 just to parse that style sheet. Or it could have done an entire lap of Saturn's equator whilst a Moto G4 was simply parsing that style sheet. One thing I have to admit is when I was researching this part of the talk, I learned way more about how fast light is than I did about how slow a Moto G4 is. So take it with a pinch of salt. But 1/5 of a second, certainly in sort of performance optimization terms, is an absolutely gargantuan amount of time. And slower devices are going to have to deal with that, and there's nothing you can do about it. It's completely divorced from network cost. Even if that file's come out of cache, the browser's still going to have to parse it every time it's loaded into memory. So it's something to really be aware of is file size has, yes, network costs, but hidden runtime cost as well. A really great way of making files bigger is to jam them full of base64 encoded assets. So many years ago, we were told, perhaps stop doing the top version and start sticking your assets inside the style sheet by base64 encoding them. And this advice was given with the best of intentions. People were thinking, well, HTTP1, we've got a limited number of connections we can make at any given time. Only 6 connections at a time to a given origin. Why don't we stop wasting those connections on images and actually put them inside the style sheet? And this was advice given to us with the best of intentions. But the problem is there was a hidden cost, and this was actually the wrong thing to do. Because what we're doing now is we're just loading style sheets, these render-blocking assets, with heavy, heavy information. This is what the FaCSSt logo would look like if we were to base64 encode it. FaCSSt do not do this, so I'm not dissing them. I'm just saying this is what it would look like if they did, and that would be a bad idea. Because base64 is, yes, now considered an anti-pattern. Not only does base64 increase the file size of critical assets, that increases at the exact worst point it possibly could be, because it's on your critical path. The wonderful thing about images is they turn up whenever they're ready. A browser will render a page with images missing. However, it will not render a page with CSS missing. So if you're making your style sheets bigger and bigger and bigger, what you're doing is you're just moving non-critical assets directly onto the critical path. You're moving these assets to the worst possible place. I did a bit of an experiment, I believe, late last year or earlier this year. You're about to see some really bad graphs, some really bad data viz. But the reason they're bad is it helps me prove my point a little bit. You'll just have to trust me on that. But the experiment was I took a regular image and a base64 encoded image, and I built the same test case with both of them. I wanted to look at the CSS parse time, the image decode time, and the first paint time of each method across desktop and mobile browsers. What I really want to focus on is the first paint time, because that's a very user-facing metric. How quickly could we get something in front of a customer? What you'll notice here is that on desktop, we were spending a lot more time, on first paint, almost double the amount of time. Over double the amount of time. base64 performed much worse in all categories on desktop. And that was a fairly high-powered desktop machine. So that was actually this machine right here. What I then decided to do is rerun these tests on a Moto G4 and see just how much more expensive base64 encoded assets were. And what you'll see now is that we're spending 10 times longer getting to a first paint by moving those images into our CSS files. Leaving those images separate meant we could start rendering the page over 10 times sooner. Just pulling these findings out into something a little more digestible. On desktop, parsing a style sheet was 10 times slower if it was base64 encoded. On mobile, parsing the style sheet was over 32 times slower if that style sheet was full of base64 encoded assets. On desktop, first paint was over twice as slow with base64 encoded assets, and a staggering 10.27 times slower for first paint on a mobile device. Simply moving images from image files and into CSS had a cost of over 10 times more for first paint. As a user, you feel this, right? You're looking at a blank page. I think the difference in time was it was 700 milliseconds with a regular CSS file, and it was 7 seconds with a base64 encoded file. This is tremendous. This was absolutely enormous. And that's a cost that we're just passing straight on to our users. If you're, I guess, particularly bored, you can read the full case study here. All the Google Sheets, all the kind of raw data is there. You can kind of mine through it. But suffice to say, in nearly every single scenario, base64 encoding assets is going to be an anti-pattern. It's worth doing a quick departure. The reason base64 is so bad is it doesn't gzip very well. It's kind of not very sort of susceptible to high compression. If you're embedding SVG data inside an HTML document, it's a completely different story. So embedding an SVG in your HTML is generally going to be fine, so don't panic. It's specifically talking about base64 in CSS or HTML. So that's the kind of thing we need to worry about. At import, and I'm not talking about SAS import here, I'm talking about the sort of vanilla CSS at import directive. Who's used one of these before? I know I certainly have. These are frequently used for things like Google Fonts, right? Keep your style sheets all nice and self-contained. And this is usually done for kind of neatness sake. However, it turns out that this, again, is an anti-pattern. At import has quite big network delays, and it causes first render to be delayed quite significantly. I was working with a client recently who'd done something a little like this. And actually what they'd done is they'd done this for kind of good performance reasons. They'd identified different discrete sections of their CSS project and thought about how they would want to cache and indeed cache bust those parts of the project. Your reset never changes, so cache it very aggressively. Typography should seldom change, same as grid, so maybe we should cache bust those slightly infrequently, but your components, maybe they change with every release, so we can cache bust your component CSS separately. However, the way they implemented it, by using imports, led to quite drastic delays in the first render. I pulled this out into kind of like a reduced test case. What you can see here quite clearly is this first file is kind of an orphan download. That first big, my pointer isn't working, but this first big blue file here is an orphan download. It's just nothing else is happening in parallel. Completely wasteful. I didn't need my pointer at all. I'd circled it. So here we can quite clearly see very sequential downloads. It's not until the first CSS file is being downloaded that the browser reads it and says, oh, shit, there's more CSS, and it has to go back across the network and get more stuff. The actual site in question looked like this. What you can see with these files here is they're the last things that get downloaded before start render. That vertical green line is the point at which the browser started rendering the page, and all of these CSS files are blocking that moment. Unfortunately, all of these CSS files were stuffed inside another CSS file, which was causing quite severe network delays. Basically, this was the paradigm we were getting. What the browser would really like to do is, at the point it has received style.css, is start building the CSS object model and begin building that render tree. However, as soon as it opens style.css, it finds references to 4 more style sheets, which has to then go back over the network and pause CSS construction, CSS-OM construction completely. The CSS is kind of coming from inside the CSS. Now, the way I fixed this and made the site about half a second faster was just by swapping out to this. I went through this in my workshop yesterday. Never tell your clients what you actually do, because if I'd have told them this, I would have not got paid. All I told them is, well, I restructured your CSS in such a way that the site is half a second faster. Pay me. But it was simple. I just flattened these out into link rel equals style sheets and away from imports, and the site did get half a second faster. And you can see that as evidenced here. This particular test case wasn't half a second. It was 412 milliseconds, I believe. But still, train line 0.3 seconds, or 300 milliseconds is worth 8 mil. Here we can see how quickly we can start getting these gains. Next thing I want to look at is selector performance. A talk on CSS performance wouldn't really be complete without talking about selectors. Anybody know much about selector performance? Like how fast or slow individual CSS selectors might be? A couple of you, a little bit. Well, I'm kind of glad you don't know much, because this is the last thing on your list of things to optimize. Browsers are incredibly fast at matching and parsing selectors, so don't stress about this too much. The good news as well is if you use a componentized architecture or use a naming convention such as BEM, you're going to be writing fast selectors anyway. So the good news is if you're writing like what we'd consider good CSS, that will also generally be fast CSS. But let's take a look. There's a very key and very important distinction or important thing that happens inside a browser which governs your selector performance. And that is the fact that browsers read selectors from right to left. They don't read from left to right like we do in the West. They actually start at the end. They start here. Who knew that? Oh, sweet. So people don't know much about selector performance. Look at all those hands going up. Now, the reason the browser does this, I think, is remarkable. I think it's one of those beautifully simple design decisions that I want to meet the person who did this and buy them a drink. I think it's so smart. But this is called your key selector. This is the bit we actually care about. This is the bit the browser is actually going to style. Everything to the left of this is just conditions and caveats. They're effectively if statements. If it's inside this, if it's adjoining this, if it's a class on this element. The key selector here, the thing on the end, is the thing we actually care about, and it's this that will hold the key to your performance. Now, the reason the browser starts on the very right-hand side is it wants to know if that DOM node even exists. There's no point starting a selector if the actual class on the end of the selector doesn't even exist in the HTML. Now, the analogy I use here is when you were a kid, you may have played games like this. When you were a child, you may have played games where you've got a pot of money and you've got 3 different routes to get there. Now, you're 8 years old, right? You're busy, you've got stuff to do, you don't have time for this kind of crap. So what you do is you cheat. And what you do is you start at the end, right? You start here and work backwards. If you start at the left, you've got a 33% chance of getting this puzzle right. You start at the bag of gold, you're going to get back 100% chance of getting it right, okay? So basically, the browser is doing the exact same thing. The browser skips to the end, and it looks, hey, this class isn't even in the HTML, so I know for a fact that this selector could never possibly match, and it doesn't have to do any of the subsequent work. That simple inversion in logic, that simple starting at the right-hand side, really quickly allows the browser to say, well, these classes, these selectors couldn't possibly work because these classes aren't in the HTML, and it can quickly discard whole swathes of CSS and move on to stuff that is more likely to have a match. Individual selectors then have an inherent performance. So classes are really fast. So something like nav item is going to be a pretty fast selector indeed, because when the browser parses the DOM, it tokenizes it, and it creates like a hash table of all the IDs, all the classes in the page, and these are very, very quick to find. By comparison, something like sidebar P is a little slower because the browser finds every P element in the page and then checks if any of them live anywhere inside a sidebar. There'll be a lot of false positives there. There'll be a lot of things that don't live in a sidebar but are a P, so it'll have to probably select maybe 100 elements, and maybe only 3 elements end up matching. So you'll get a lot of waste there. Something like icon star will be much slower because the star selector finds every single DOM node in the page. It finds your link rel equals style sheets. It finds your head tag, right? It finds your title tag. It finds every single DOM node in the page, and it asks every single one of them, do you live anywhere inside an icon? Not just directly inside an icon, but anywhere inside. Therefore, this is, by comparison, I cannot stress this enough, by comparison, a very slow selector. In absolute terms, it's still pretty fast, so don't stress about this stuff. Years ago, when we started moving to the global box sizing, kind of star box sizing border box model, people were stressing out. Like, the star selector is really slow. We can't use the star selector for this. Actually, it's not true. The star selector on its own is actually really fast because it's the quickest way to select everything on a page, right? If you want everything on a page, then the star selector is the absolute correct way to do that. So a bare star selector is actually going to be really fast, but a star selector at the end or in the middle of a compound selector, it will be comparatively quite slow. Quick quiz for you then. Which one's faster? Put your hands up if you think the top selector is faster. Okay. Put your hands up if you think the bottom selector would be faster. Slightly fewer hands. And put your hands up if you're genuinely not sure. Yeah, there we go. The answer is the top one. And the reason it's the top one is because we're only checking one level of the DOM at a time. We start at the very end with the A element. We ask the A element, hey, is your parent an ally? And if the parent isn't an ally, we can just cancel out straight away. With the bottom one, we're not asking for a parent, we're asking for any ancestor. The analogy I use here is the top one is like asking me, hey, Harry, is your dad called John? And I have that information ready to hand. I'm like, no, he wasn't. He isn't. I hope wasn't. It's his birthday today. I hope he's still with us. Yeah, my dad isn't called John. However, the bottom one is like saying, hey, Harry, was any of your male family tree called John? And probably, I'm British, but I don't know for definite. It would take me months to find that out. So the kind of comparison I use there is, it's the family tree thing, right? So don't run to the office on Wednesday and start rewriting your CSS to look like the top one, but the top is technically faster because we're only quizzing one level of the DOM above us. The bottom one has to go all the way up the DOM tree until it either finds a match or it reaches the root element, which is probably your HTML tags. Many, many years ago, in a browser called Opera, anyone heard of Opera? That's a bad joke, I'm sorry. In a browser called Opera, they had some tooling called Dragonfly. Did anyone remember Dragonfly? Yeah? About 3 of us. Dragonfly had this amazing bit of tooling where you could actually look how long each individual selector took to parse, how long it took to look up. Even this, from goodness knows how many years ago, you can see how fast these selectors are. It's not worth optimizing. 0.004 milliseconds isn't something we need to stress about. But I find this actually really fascinating, just knowing what's going on, seeing how long this takes. Now, who would like to see this in Chrome? Just like, what, 8 of you? Forget it. Well, it doesn't matter anyway, because it doesn't exist. You can't do it in Chrome. However, if you would like to see this in Chrome, please take a picture of this slide right now while I take a drink. This is a product forum discussion thing for Chrome developers. Me and a bunch of the devs have gone in here and said, hey, can you just build this thing into DevTools? It used to be in Opera years ago. So if you go and you just put a +1, tell them that you're interested in the feature as well, we might be able to start measuring individual selector performance inside of DevTools, Chrome's DevTools. I'm not a total bastard. I'm not going to leave you completely empty-handed. I'll show you how to proxy this information. I'll show you how to get this information very roughly. It turns out that a recalc style event in DevTools, in Chrome, roughly 50% of that time is spent doing selector matching. So any recalc style event you see in your performance profiles, 50% is doing CSS OM construction, building the CSS OM, working out, okay, this has a higher specificity, this inherits from this. The other 50%, roughly, is spent doing selector matching. So any recalc style event, you halve it, you're going to find out how fast all of the selectors were as part of that event. For example, on my site, the entire homepage, the recalc style event was just 14 milliseconds. Halving that, 7 milliseconds spent matching every single selector on an entire website's homepage. This stuff's really fast, right? We really didn't ought to go out of our way to optimize for this. Browsers are doing that for us. However, I'm also quite keen to stress that if you're writing component-sized CSS, it will be fast by default anyway, so you're going to be getting this kind of for free. Oh, right, what next? This is like a bit of a tour of everything I know about CSS performance, really. I hope it's digestible enough. Alphabetic CSS. Who writes their CSS in alphabetic order? Like declarations, you know, align items first, Z-index last? Okay, get out. Disgusting. Yeah, honestly, I'm beyond caring. I don't mind what you do, as long as it's consistent. However, yeah, it turns out if you write your CSS in alphabetic order, you're going to have a faster website. However, I can't stress this enough. If selector performance was the last thing on your list of things to optimize, this isn't even on the list. But it is quite interesting. It is quite interesting as to why this happens. If we were to take a declaration like this, sorry, a rule set like this, that's written in a somewhat random order, and alphabetize it, what we're going to find is that our compressed style sheets will be a little smaller. gzip really likes repetition. gzip really likes consistency. So if we're always writing our CSS in a predictable, consistent order, gzip will be more effective, but not by much. If I bust out my microscope, I'm going to find out that it's about 3% smaller. Oh, see people taking a picture of that. Oh, there you go. It's a saving of about 3.25%. But, however, like, well, I was thinking about this, we mentioned it in the workshop yesterday. 3.25%, I mean, 3.25% of a big number is a big number. So if you're operating at Facebook or Google scale, maybe a simple sort of build process to alphabetize your CSS and saving for free about 3% file size, that might be non-trivial at that kind of scale. So maybe it is worth considering if you're operating at an absolutely vast, kind of unimaginable scale. But yeah, interestingly, yeah, I was surprised to find it, but alphabetizing your CSS will make it small, will make your site faster. What I'll do is really quickly explain why this phenomenon occurs with a very crude, very oversimplified introduction to how gzip works. So gzip takes strings of text, and it looks for repetition and consistency, and then it will try and store that text in a smaller way with 100% retrievability. So if we've got a string like AAA, BBB, CCC, we could store this much shorter by saying, well, 3A, 3B, 3C. We've now stored it as 6 bytes, for argument's sake, instead of 9, and we can still fully retrieve all of the data here. We just expand this simple algebra, and we get completely lossless compression. This is what happens if you have alphabetized or consistent order in your text. Conversely, if this is randomized, CBC, AA, BB, AC, We can't compress that down by much at all. I think the closest we could get is CBC 2A to BAC, right, which is the exact same amount of text. So this is exactly how, well, no, this is not exactly how gzip works. Sorry, this is a model for how gzip works. It's a very crude oversimplification. But this is the same of any text that you write. Like micro-optimization is central, but if your attributes on your HTML elements, always do href and then title. Don't do sometimes title href, then href title. It goes right the way through to your HTML. Writing things in a consistent order will give gzip more chance for compression. It's called your compression delta. So yeah, gzip loves repetition and consistency. Next one, mix-ins versus extend. So I've got opinions, strong opinions on mix-in versus extend, but it turns out there's also a performance-oriented decision to make here. One of these will be faster than the other when it comes to network performance. Who thinks mix-ins would be better for performance? Who thinks extends would be better for performance? Who genuinely isn't sure? Yeah, that's fair. Let's find out. So I built a very, 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 very oversimplified test case to demonstrate this. I built the exact same feature, once using extends and once again using mix-ins. Now in SAS, the extend version was 20 lines of code, mix-ins was 24 lines of code, but of course, we don't care about file size in pre-compiled assets. It doesn't make any difference to us. So once I compiled both of these out, I found that extends went down to just 18 lines of code, whereas mix-ins shot up to 30 lines of code. Quite a big difference there. Mix-ins make much larger files because we're just repeating stuff over and over again. So who thinks mix-ins are better for performance? Who thinks extends is better for performance? Roughly the same as before. Turns out that mix-ins are going to be quite a bit better for performance because once you gzip this file, because gzip loves repetition, we've got way more repetition in the mix-in version of this feature than we do in the extends version. Extends repeats a couple of things twice, whereas the mix-ins repeats a load of things several times. Your chance for compression, your compression delta here, is much, much larger. In fact, to the tune of, I think, in this case, it was 23%. We had 23% better compression by using the much larger mix-ins once we deployed gzip. So yeah, mix-ins are better for performance. Mix-ins will, over the network at least, be faster because they produce much smaller compressed file sizes. But that was a very non-scientific demo. So what I did is, sometime, I think either last year or the year before, I took an existing real project and I quickly refactored it to use all mix-ins, then again to use all extends. So on a real project, we saw very similar results. In fact, the results were slightly better on a real project. Mix-ins were, as expected, far larger on disk, weighing 108 kilobytes versus extends 72. But after I gzipped both of these files, the tables turned. Mix-ins went down to 12 kilobytes, whereas extends only got down to 18 kilobytes. Now, if anybody's heard of the magic 14 kilobytes when it comes to sort of TCP IP performance, we looked at that in the workshop yesterday, there's a magic 14 kilobytes. The first kind of brand new TCP connection's maximum sort of bandwidth is limited to 14.6 kilobytes. So on a new TCP connection, the first round trip can only carry about 14 kilobytes worth of data. What's happened here is a critical asset has snuck beneath that threshold, means we can get 100% of this CSS from the server to the client in one round trip. With the 18 kilobytes on a brand new TCP connection, we would immediately have to go to 2 round trips of latency to deliver all of the required sort of assets, the required packets. It's in really bad taste to quote oneself on a slide, but it's too late, I've done it. What ended up happening here was we achieved in kind of this realistic scenario about 27% better compression deltas using mix-ins, which did result in obviously larger files on disk. But after gzipping it and over the network, it's roughly a quarter is what you should expect to achieve in terms of savings. This tip is potentially the most contentious and currently at least tested in this entire slide deck. Because the case study came from a couple of years ago, and we've got plans and ways of mitigating the problem now. But this is a thing that happened to me a few years ago when I was working for a company called Sky, quite a big broadcaster in the UK. In fact, I was working for a company called Sky Bet, right? Sky Betting and Gaming, who has recently been bought by a Canadian company, so I guess it's yours now. We're working for Sky Bet, and we were working really fast sprints on a brand new mobile application, m.skybet.com. This is how old I am. This is before responsive design. m.skybet.com. And we were building really quickly, and the host domain, sky.com, or skybet.com, sorry, was getting overloaded with assets. We were running on HTTP 1.1, which meant we could only download 6 files at a time from that domain. So we decided, right, well, let's create static1 and static2.skybet.com and download 6 assets from each of those in parallel, therefore achieving better performance. So we moved from this kind of paradigm to this kind of thing. We've started putting our static files on these static domains, st1 and st2.skybet.net. And what we did is thought, well, brilliant, now we can start downloading an extra 6 assets at any given time. We're going to be much faster. We put this live, probably went to the pub, congratulated ourselves, rocked up to work the next day, probably slightly hungover. And what we did is we had an automated web page test that would run every night and tell us how performance had changed day on day. So the performance engineering team, we got this web page test result in front of us. We were shocked to see that the site had got slower overnight. Things had got worse. We were perplexed because the last thing that went live was a purely performance-oriented change. What happened is this. Because we'd moved the CSS file onto a brand new domain, we had to now do new DNS, TCP, and TLS negotiation. We had a lot of network overhead right in front of this critical asset. So it took us longer to even find out where the CSS lived. This was causing delayed first paint, which was making the whole site feel slower for customers. And in the worst case scenario, quite high latency, it was to the tune of hundreds of milliseconds. The simple fix was, right, we identified any render blocking assets, so any CSS and any JavaScript that was needed to render the page. We moved those back onto the host domain. So we just moved those back onto skybet.com and left any really non-critical assets, such as images and deferred JavaScript, we left those on the asset domains. And that was about the fastest possible way we could achieve this. Nowadays, there are different ways to mitigate this. The first one would be just use HTTP2, and you don't need to use domain sharding. The second thing you could do to mitigate this, if you're not running H2, is to use resource hints to pre-connect these origins. So if you just want to type resource hints down somewhere, you'll find some information there. I've got 10 minutes, so I'm going to have to start hurrying up. The only other person who's really talked about this, moving CSS off of asset domains, is a guy called Stoyan Stefanov, and he said, make your CSS small, minify it, compress it, load it from the same host name, brackets, no DNS. So removing that network delay, that network overhead, can make the site render a little quicker. My second favorite tip in the entire slide deck, the favorite is right at the end, is this one, and this is quite a new one. It's so new that I'm going to have to refer to my notes quite a lot. I'm really lazy, right? And I wanted a more pithy, kind of a better title for this slide, but it was too long to fit on one line, and I couldn't be bothered redesigning the title slides to work on broken lines. Typical like design approach, like, well, we'll just assume the content's correct. So link in body isn't the best title for this, but what I'm going to talk about is the fact that nowadays, in all major browsers, you can now put your link rel equals style sheets inside your body tags. They no longer have to live in the head. This has huge, huge ramifications when it comes to rendering performance. Traditionally, all link elements must go in the head, but nowadays what browsers have decided is they will permissively allow people to put link elements inside the body. It would still technically be invalid HTML, but the browser's parsers will accept this and react accordingly. And what this allows is for us to effectively, progressively render pages. Traditionally, what we may do is this. We've got one big app.css, this one big bundle that's got all of the site's CSS in there. This is what you do with HTTP 1 or 1.1. But the problem here is the browser can't render any of the page until 100% of app.css has been downloaded. The problem we've got here is that there's probably a lot of redundancy in app.css. The entire site's CSS is probably way more than is needed for this particular page. The second problem is this will block rendering. We can't render the page until 100% of this file has arrived, even if we only need 5% of its contents. So browsers don't render anything until all CSS has been retrieved. This means that the browser can only render as quickly as your slowest CSS file. So with HTTP 2, what we can do is split everything out. Instead of having one mega style sheet, we can start being a little more selective and start passing a little more appropriate payloads for the page. This solves the redundancy issue. We're loading about the correct amount of CSS that we should be, but this still blocks rendering. The browser won't render any of the page until all of those style sheets have been retrieved. A browser is only as fast as the slowest style sheet. So now what browsers have decided, though, is amongst them all, Safari is the only odd one out. Safari is the new IE. They only block rendering of subsequent content. So rather than blocking the rendering of the entire page, they will only block the rendering of the HTML underneath the link rel equals style sheet. What that means is if you move a link rel equals style sheet down the HTML, the browser will render everything it can until it finds the link rel equals style sheet, pause rendering, download the style sheet, then render the rest. This means that we can now move to a pattern like this. The browser will render, find a style sheet and pause, render, find a style sheet and pause, render, find a style sheet and pause. This now allows us to do very progressive rendering of web pages, and you can actually see it coming together. This is pretty nice, it's pretty sweet. So here's a video of the before, right? The before scenario is, I'll let people grab a quick picture of this. The slides are already online, so don't stress too much if you don't get a picture of this. A little video here. Nothing, get to about 3.9 seconds, nope, well, whatever it was. We see nothing, then the final style sheet arrives and the whole page renders in one go. The browser is only as fast as the slowest style sheet. This is bad. What you can see here is that it was actually footer.css that was the slowest file. The footer wasn't even in view. We couldn't even see it in that video, but we didn't render the page until that footer style sheet had arrived. With the new change in browsers have done this for us. We don't need to really do anything to adopt this new sort of functionality. We get a rendering that looks more like this. The browser finds a style sheet, pauses, downloads it, renders the rest, pauses, finds the next one, renders the rest. What this means is that all of those style sheets were pretty slow. Looking at this waterfall chart, nearly all the style sheets were problematic here. But the browser could start rendering after it found each one. What this means for UIs now is that if you're especially if you're using a componentized architecture, putting your link rel equals style sheets in line above that component, you can start to progressively render web pages. This slide is marginally out of date. I apologize. This is about to go live in Chrome 70, which is the next one coming. But Firefox and Edge/IE will give you a lovely progressive render, whereas Chrome and Safari give you a white screen until all the CSS loads. That first paragraph sounds great, right? Apart from the bit where it'll give you a white screen. That sounds terrifying. Second paragraph helps put our mind at ease. The current Chrome Safari behavior is no worse than putting all your style sheets in the head, so you can start using this method today. What this means is nothing will ever get slower. It just means that browsers that support this new behavior will get faster. This is completely progressive, and you can start using this right now. Actually, so what happened is Canary shipped this in 69, so it's already live in Canary, and Chrome 70, normal Chrome 70 is coming next. It won't be behind a flag, so it means that all major browsers, except Safari, do this immediately. They do this already. So you can start using this today. It wouldn't be a cool new feature if there wasn't a bug, so we've got to Firefox fix this. Sometimes Firefox just doesn't do this. Sometimes it will just keep rendering before it's downloaded the style sheet, so it won't actually pause. What that means is that users could see a flash of unstyled content, a flash of Times New Roman or whatever. So what we need to do is force Firefox to pause when it finds the style sheet. The way you do that is pretty grim. It's pretty ugly. Just drop an empty script block just after the style sheet. Now, this leads me really nicely into my last little section, because what we're seeing here, is completely standard and spec'd behavior, and it is a huge thing that I've never met a developer who's already known this. What I'm about to show you is fundamental for fast websites. The reason this works is that no browser will execute a script block whilst it is currently downloading any CSS. If a browser is currently downloading any amount of CSS, it will refuse to execute any inline script tags. Who knew that? Who wasn't on my workshop yesterday? There we go. There we go. A couple of people. This is fundamental. This is huge, huge, huge news for how fast browsers can render pages. Your script won't execute if CSS is still downloading. That means that client with a 1 meg style sheet, if that 1 meg style sheet takes 3 seconds to download, that's 3 seconds the browser will refuse to run any inline scripts. Knowing this, we can speed our websites up tremendously. So loading CSS and JS is the last section, I think probably my favorite. This isn't CSS in JS. Don't have time for that holy war. This is loading CSS and JS in a page. The proper way of wording this phenomenon is that inline script block on CSS on construction. Or put more simply, inline script will not execute if the browser is currently downloading any CSS. The reason for that is that inline script could be asking the browser, hey, what color's the page? The browser won't know what color the page is if it's still downloading the CSS. So what it will do is it'll finish the CSS, build the CSS object model, then it will allow the script to run. And if the script asks, hey, what color is the page, the browser can give it a proper, true answer. However, nearly all JavaScript that appears in script tags isn't going to be asking any CSS-y questions. So for the most case, this behavior is actually slowing us down. And there's a really simple fix. You've probably seen code like this before, these async snippets at the bottom. These are designed for performance reasons. Let's create asynchronously, let's create dynamically create a script tag, download that asynchronously, blah, 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 blah. Things should be fast. Now, what most developers do when they implement these, because these normally come from third parties, is try and put them near the bottom. If you've ever read Google Analytics documentation, it says, hey, put this script tag near the head of your document. Every developer's like, no, I don't think so, buddy. I'm not doing that. I'm going to put you down at the foot, right, near the closing body tag. I know what you're trying to do. It turns out that Google Analytics are completely correct to tell us to do this. If we have any script tags after a style sheet, we get this, completely sequential downloads. You can see quite clearly here that this JavaScript file didn't even begin downloading until the very second the CSS had finished. We've completely lost any parallelization here. Luckily, the fix is simple. We take our head tags and just swap that around, and boom, we get this, complete parallelization. Here's another thing of don't tell the client. One of the first things I'll do when I'm doing a performance project is just spend half an hour with a coffee and some tunes, just reordering my client's head tags, and then just cut them an invoice. It sounds trivial, but this has huge impact. Just knowing that scripts will not run if a browser is currently downloading CSS has a massive effect on the way you think about how you structure your web pages. So reordering your head tags to take care of this or to be aware of this can have hundreds and hundreds of milliseconds, up to seconds, depending on what the actual assets are, of performance improvement. These async snippets, these are an anti-pattern. Don't use these anyway. These are bad now. These existed to polyfill lack of support for the async attribute. Nowadays, we just use JavaScript. Just use the async attribute for loading JavaScript files. Don't bother with async snippets anymore. Browser support for async is perfect because we don't count Opera Mini. So yeah, use the async attribute, try and move away from these async loaders, and just make your pages faster. So we're going to try and wrap up a 103 slide talk in one slide. Basically, optimize your critical path, right? Make sure it's not too heavy, make sure there are no redirects in the way. Keep blocking CSS to a minimum, avoid base64 except for a tiny handful of exceptions. Take a picture of this in a second when all the notes are on there, because it'll probably make a bit more sense. Import is evil, don't use import. Extends is evil, but for many reasons other than performance as well. But specifically for performance, mixins are better. Alphabetic CSS is better, but only for performance. It's horrible. Alphabetic CSS. And finally, get your head straight, right? Look at your head tags. Make sure that your CSS isn't blocking any subsequent resources such as JavaScript. And I'll wait till you've taken a picture. Not of me, of this. Cool, you got 3, 2, 1. Thank you very much for listening.